Hello everyone. Today I'm glad to present you my research in the study of application of metric learning to large-scale image classification tasks. First of all, let's review how classical approach may be applied to solve such an classification task. Usually, it is solved by training an end-to-end model, which actually consists of two parts, namely feature extractor and feature classification. Thus, having labeled datasets in terms of each sample have a corresponding label, we can train it to end-to-end manner using backward propagation. So such approach allow us to classify image using one forward pass through the network in inference time. But for training, it requires a large-scale dataset. Uh, Actually, such dataset exists, for example, ImageNet or OpenImages, but despite existing such large-scale datasets, a lot of classes are still uncovered. Moreover, creating such large-scale datasets may not be available at all for some business cases, like supermarket, where object are changed very quickly from, for example, day by day. So, what about metric learning? It works in completely different manner. It consists only from one model, one feature extractor, and we expect to train that feature extractor in such a way that having extracted embeddings from two images, we can it compare in some metric space, and if such embeddings are similar in that space, we can assume that input images were similar as well. So having a pre-calculated database of such embeddings, we can extract embedding from one input image, find the similar image from our database, and predict the label of input image based on a label from our database. Our work is focused on using a triplet-based metric learning approach. It mainly focused on using triplet loss function. So the idea of such triplet loss functions is pretty similar. It deals with three input images or three input embeddings of those images called anchor, positive, and negative. So anchor is just a random sample from our database. Positive is also a random sample from our database, but should be exactly the same class as an anchor sample. And similar to that, negative sample, it's also a random sample from dataset, but should be any class, but should be differ from anchor and positive class. So we should calculate distance between anchor and positive, between anchor and negative, and our loss is consist of differences between those distances plus some margin that is used to control what level of similarity satisfies our training process. So minimizing of such loss, we will force by minimizing such loss, we will force to our model to extract embeddings similar for in terms of our matrix used here, similar for the same classes and different from for different classes. Our work were focused not on large-scale datasets like ImageNet or OpenImages, large scale in terms of available number of images, but number of classes still the same as in ImageNet. We used FSS 1000 datasets. It is collected to be similar to ImageNet, but having exactly 10 images per classes, and authors of the datasets avoid any biases between images. For example, if it says 1000 dataset doesn't contain hundreds of images of breed dogs, unlike ImageNet dataset that does contain. Originally, the datasets were collected for image segmentation task, but we inspect the dataset and found that only one class are presented per image, and usually those object per image fit more than 80% of image itself. So we crop all those images and convert the dataset for image classification to image classification task to be suitable for that task. We built a triplet-based model using EfficientNet V2 baseline, actually pre-trained on ImageNet. Also, we add one more layer, fully connected layer, called embedding layers of size 256. It actually is the size of our embeddings. And also on top of that, we add a L2 normalization layer to keep all the embeddings the same scale. We split our dataset in such a way to keep 7 images per train and 3 images per test for each class. So we came up with a perfectly balanced dataset. And on this graph, on the slide, on bottom of the slide, you can observe losses obtained during training our model using triplet loss. On dashed, there are training loss, and solid line stands for validation loss. We trained our model in 2 stages. The first stage is just fine-tuned, fully connected layer, embedding layer, using knowledge transfer process. On the second stage, right on this graph, we unfreeze the whole model and find and train the whole model to the end. After training, we calculate our embeddings from obtained model, and we observe that obtained embeddings are perfectly normally distributed, except that 0 outliers, because it's very easy samples. And we found that such embeddings may be easily divided into 2 groups, and we performed just auto thresholding and found the threshold. So below the threshold, we assume that images are the same, and under the threshold, images are different. Following that approach, we achieved true positive rates more than 92% and almost 100% for true negative rates, which is very, very good result, actually. But we will move on, and we will talk about classification of such embeddings. So we found that KNN models may be the perfect candidate to much similarity to much similar embeddings in some metric space. We used 7 nearest neighbors. That number was evaluated during cross-validation. And after applying nearest neighbor classifier on top of extracted embeddings, we achieved more than 83% of top 1 accuracy and almost 96% of top 5 accuracy, which is much better than vanilla EfficientNet V2, our baseline. We also performed an ablation study and found it very important to choose a triplet mining policy correctly. For example, on left graph, you can observe, on left image, you can observe confusion matrix between each pair of classes. And those graphs expose to us a mean distance between classes in terms of embedding distances. So random triplet mining leads to completely failed training process because there are a lot of confuses between different classes. But when we use a hard triplet mining, it means that during training we only consider training on those triplets that have quite big loss, or in other words, it doesn't care of those triplets which are already was classified correctly. So following that approach, our confusion matrix are much smoother and it leads to dramatically better results. So, as a conclusion, we found that triplet-based magic learning models may be easily applied not only for face recognition and similar tasks, but also may be used for classification daily objects, and even it is suitable to classify a novel object, which actually is our further research. So, thanks for attention.